Welcome back, everyone. I hope you had a nice lunch break and you've got your coffees and stuff. The next talk is going to be given by Hans Chan, and he's going to be talking to us about excited state calculations on small molecules with an adaptive ansatz for quantum computing. So whenever you're ready.
Great. Thank you, Josh. Hello, everyone. And thank you for having me at this workshop. And of course, big thank you to the organizers for putting this event together. In this talk, I will showcase some of the new methods that we've developed to reduce the quantum circuit depth needed in encoding molecular excited state wave functions on quantum computers for energy calculations. And so for the benefit of those just tuning in, because I'm pretty sure my parents will be watching this, but also for any chemists new to the field of quantum computing, I will start with a chemist perspective of excited state variational algorithms. In recent years, computational studies of excited state chemistry are seeing more and more use cases in topics like ultra-fast spectroscopy, novel cancer treatment designs, photovoltaics, and even tackling atmospheric pollution. The first step to studying excited state chemistry is, of course, to accurately find a molecule's ground state and excited state energies as a function of the arrangement of atoms within the molecule. This generates these multi-level potential energy surfaces, as you can see in the animation, which gives us information about how a molecule's energy would change given an adjustment in its geometry. Specifically, we are obviously trying to find the low-lying eigensolutions to the time-independent Schrodinger's equation at different geometries of the molecule. In excited states chemistry, the ab initio approach is still the best way of doing this accurately and systematically. However, as we've heard from earlier talks, and as we all know, ab initio methods converge slowly with the size of molecules. Both the classical computing memory and the computing time scale prohibitively for the most accurate methods, making them out of reach for the large and interesting molecules that people really care about. And so the reason why we're all here today, I hope, is that we agree that quantum computers have the potential to address these scaling challenges because molecular wave functions are by their very nature quantum information. And so a quantum information machine should, in principle, be better suited at simulating them. Specifically, in the near term, we might expect to see the offloading of the wave function processing and simulation to QPUs. I like to see it in many ways similar to offloading graphics processing to a dedicated GPU. You would use a quantum circuit to prepare the computer such that its state matches that of the molecular wave function. You would then apply Hamiltonian operators directly onto the wave function that you've just prepared, and finally extract the energy eigenvalues of the Hamiltonians by measuring the values of the qubits. The flagship algorithm, as we all know, has been the hybrid VQE, where you would first split the molecular Hamiltonian operator into Pauli operator terms, these P's here. And each of these terms translate onto a chunk of quantum circuit. And you'd express the molecular wave function as a parameterized unitary U applied to some reference state, often the Hartree-Fock reference. This ansatz U basically determines how close to the real system you are and how accurate your energy calculations can be. Being physical chemists, we want this unitary to be physically motivated, in other words, based on the features of real physical systems. And so the unitary version of the couple, cluster, singles, and doubles method, given its ubiquity in molecular physics, is often the go-to. Talks from this morning give more in-depth justifications for this choice, so feel free to refer back to them for more detail. And with some approximations, what we call drosselization, this unitary is split into a sequence of Pauli operators, which maps directly onto a parameterized circuit along with the reference state to give you a simulated wave function. One would then use a plethora of strategies developed, some of which we have heard about already in this conference, to compile this Ansatz circuit into a more economic form to basically reduce the gates needed to achieve the same state preparation. And so if you whack the Ansatz and the Hamiltonian terms together, you can start running energy measurements on a quantum computer. The Ansatz circuit is applied to each Hamiltonian term. The energy is measured multiple times per term to get an average. And you repeat this for each Hamiltonian term and tally up all the contributions to get your total energy. all that's left for a classical computer to do is to run some standard SCF calculations and tuning the parameters in the quantum circuit so as to improve the quality of our simulated wave function and the accuracy of the energy calculated. What we have been particularly interested in is the extension of the VQE to recover excited states energies as well as ground states in a new method published last year. We've already heard a lot about this amongst other methods for recovering excited states in the first talk yesterday, so I'll try and keep this as brief as possible. We basically do this by imposing the constraint that a new eigenstate must be orthogonal to all previously found eigenstates. In practice, you basically add an overlap measurement between eigenstates into the variational minimization loop, indicated sort of by this term here. And as a result, you would recover each of the excited states sequentially. To make this method more practical on near-term noisy quantum computers, though, there are some major challenges that we have to overcome, because quantum computers, as we know in the next few years, will be noisy, and so deep circuits will probably be corrupted by random errors occurring within the circuit before the program even completes. And of course, there's also no currently practical way of correcting for that random error. In the context of finding excited state energies, that's a pretty big problem, because first, the original proposal for this method requires the use of the unitary couple cluster with generalized single and double excitations, because it's a more flexible Ansatz. So it's basically any combination, all of these different excitations strung together into a big Ansatz. Trouble is, of course, this has a lot of operators and would map into a very deep circuit. Of course, I should mention that there is the hardware efficient Ansatz and other alternatives that we have heard about in this conference so far, but not necessarily all of them are physically motivated, and so that tends to compromise the accuracy. So we want to stick to a unitary couple cluster. Moreover, the way to go about estimating overlap between states at least doubles the Ansatz circuit depth. I should also mention that there is a swap test which would do pretty much the same thing, but it doubles the number of qubits and it has a large C0 gate overhead, so it's basically even more unreasonable on near-term quantum computers. Lastly, in the original method, to find a given energy state, you pretty much have to find all of the states below it first. That adds to the number of measurements needed, which can blow up pretty quickly. And so our objective was to achieve two things. One, to reduce the number of states that we have to find before calculating higher level excited states. And two, to reduce the depth of the Ansatz circuit needed to prepare excited states wave functions such that we mitigate noise effects. The circuit depth and measurement reduction are both aspects well studied for ground states, but not a lot has been done in this respect for excited states calculations. And so what have we achieved? Well, we basically modified three features. We played around with the excitation operators used for the Ansatz. We played around with the reference states used, and we played around with the way that we string up the operators to build the Ansatz to achieve our objective. We used the following libraries to build the simulations of a noiseless quantum computer running our methods. And this, of course, is the modest system that we have been using to test our ideas on so far, the lithium hydride molecule at the minimum basis set with a groundbreaking 4 electrons and 12 spin orbitals. And so our first idea was to use the singlet or triplet reference and the subset of singlet UCCGSD operators to recover singlet and triplet states in isolation. So you can find high energy eigenstates without having to find some of the states in between. This should be a pretty familiar concept for quantum chemists because existing programs calculate the singlet and triplet states separately anyway. This also makes sense because the wave functions of different spin states exist within different subspaces of the wave function Hilbert space. So what we're basically doing is you're narrowing down the subspace that you allow your Ansatz to explore. The idea of different spin references have also been tested in other work for finding different ground states, of course. And this is just to clarify what I meant by singlet and triplet spin references. The singlet is obviously where the electrons within the molecule have paired spins, so there's no net spin. Triplet is where you have electrons with unpaired spins. And this is just a condensed form of what the singlet QCxGSD Ansatz would look like, and the algebraic form of the trotterized unitary. And so given these conditions, the QCxGSD operator, string them all up to make an Ansatz, applying them either to the singlet or triplet reference, what did we find? Well, we see that this technique is capable of finding singlet states S0 and S1 in isolation without having to find the triplet T1 state in between first. The same can also be said for the triplet states T1 and T2. So this is very promising in that we have avoided doing more orthogonality measurements for reaching higher excited states. What is not so promising is the huge circuit depth needed to make this work and the poor accuracy of the energies. The numbers quoted here in millihartries are the non-parallelity errors, basically how far away we are from the full CI. We suspect that the deep circuit depth and the poor accuracy are indeed related. There are simply too many free parameters in a very long circuit, and trying to optimize the VQE cost function in this massive parameter space is not a good idea. These plots also demonstrate one of the shortfalls of the orthogonally constrained VQE method, because you start by finding lower energy eigenstates followed by higher energy states. And so any errors you accumulate from lower energy calculations will propagate onwards. But nonetheless, we were onto something. And so then we tried using a new version of the UCC Ansatz published last year instead, and applied that to our singlet and triplet spin references. This is, of course, the k-unitary paired QCxGSD Ansatz, where you basically only include all of the single excitations and only the paired double excitations. This is then repeated k times when applied to the reference state. This has the benefit of being much more scalable than QCxGSD in terms of circuit depth. It scales k times n, where n is the number of qubits instead of n cubed in the case of QCxGSD. But it's also more flexible. What I mean by flexibility in the context of ab initio chemistry is that at the limit of k being infinite, the wave function we could prepare is actually exact. It approaches the full CI solution. And so for k larger than 1, we're basically getting closer to that, in effect, by incorporating higher order excitations. You can think of it as if we set k equals to 2, you are combining 2 double excitations to account for a quadruple excitation contribution. And this, again, is just an example of the what the Ansatz circuit would look like if we set k equals to 2. When we tried this on lithium hydride with k set to 2, what we find is that not only is this method more accurate, gives it a lot more stable behavior, but it's also an order of magnitude shorter in terms of circuit depth, simply because there are less operators and less free parameters. And I'm happy to say we're still able to avoid the spin states. You can see that you can get the T1 and T2 state without having to contend with the singlet states, and likewise for the for our singlet energy states. And so that's great, but nonetheless, we wanted to do even better than that. And so to get to our last innovation, I'll quickly introduce another new method called the ADAPT-VQE, published last year for finding molecular ground states. It's a very nice iterative method which adaptively grows the Ansatz circuit needed to prepare the wave function by sequentially selecting new operators to append to the circuit. It does this by basically defining some pool of operators to start with, for example, all of the UCC operators, and asks which operator would have the largest influence on the energy. In other words, which operator has the largest energy gradient. That operator gets added to the Ansatz, the energy is optimized, and you repeat the loop until some convergence criterion is reached, often the norm of the gradient reaching below a certain threshold. This is great because an adaptively grown Ansatz is well defined. It utilizes a maximally compact circuit, which is, of course, great news for noisy quantum computers. And it can also get systematically more accurate. The trade-off, of course, is that you need to run more measurements for the gradients. Again, from the ab initio perspective, this is very reminiscent of the k-UpCCGSD wave function in that at the infinite iteration limit, the wave function prepared will converge to the exact full CI wave function. So the more operators added, the more accurate our Ansatz is. what we wanted to do was to extend this algorithm to capture excited state wave functions and extract excited state energies. With this very compact ansatz, we can mitigate the noise, can reduce the parameter space to mitigate the effects of barren plateaus, for example, and hopefully with our latest insight, be also able to avoid the spin states when we head to higher, avoid certain spin states rather when we head to higher energy levels. And so we define a new operator selection function, which basically combines the orthogonally constrained effective Hamiltonian with the energy gradient operator. And we end up with a function, operator selection function, which has an energy gradient component and some overlap gradient component. These components can be calculated using, or measured rather, in the context of quantum computing, using the following circuits. We've already heard about the different ways of getting Ansatz parameter derivatives in this conference. This is just the scheme that the original ADAPT authors used, which I think is based on McLean. And but apart from this, there are obviously other techniques to measure gradients as well, like the parameter shift we heard about yesterday. And these are the circuits we used for estimating the overlap between unitaries. Measurement in the zero basis gives the modulus squared of the overlap. In many ways, this bottom circuit for measuring this particular component is very much reminiscent of the transition amplitude circuit we saw in Kosuke's talk yesterday morning. And so we chose the unitary paired CCGSD operator pool, with the rationale being that if the algorithm starts repeating the operator selector, that would basically mimic the K multiplier product state, and so replicate that sort of effect. It's also a smaller pool, and so less gradient measurements to deal with. And we are happy to report the animation skipped a couple of frames. But we're happy to report that this method works. You can see that when adapt finds the first state, it then adaptively converges to the higher level singlet state. And when it turns green, that's basically when it reaches chemical accuracy. So there we are. The method works. And let's go on to show this. Yes, so this, I've just picked the singlet excited states for one of the bond links to show that as we add more operators, the circuit depth grows linearly, but the energy accuracy towards the singlet excited state improves. Yeah, you can see. Okay, and so for triplets, our method also works. It adaptively gets the first triplet state to within chemical accuracy, but then unfortunately, it didn't manage to get the next triplet state, but instead converges for the triplet state above that. So nonetheless, it's still getting a triplet excited state. It just wasn't getting the ones that we were expecting. We are still trying to figure out why this is and trying to fix it, but we suspect it probably has something to do with the orbital symmetry, that our adaptive method has some hidden symmetry constraint within it on top of the spin reference constraint that we're already imposing. And you can see in this symmetry calculation done in the 70s, I think the doubly degenerate states here are of pi symmetry, but insofar as they can be determined, all the states that our adaptive method has recovered have sigma symmetry. And because lithium hydride is a linear system in the C infinite V point group, the symmetry is known to cause problems. But as molecules get more complex, these symmetry modes are less of an issue. But look, if you guys have any ideas as to why this might be the case, feel free to drop me a comment on the Slack channel. Nonetheless, the key achievement of our work is that our methods reduce the circuit depth needed to encode the excited state wave function massively. At a bond length of 2.6 angstrom, which I've just picked at random, the circuit depth reduction of ADAPT was at 96%. And in some cases, this number is even higher. This makes it obviously very promising for near-term quantum computer applications in excited states chemistry. Our methods also avoided the need of having to find new excited states only when all of the states below it had been found. And so to summarize, quantum computers, as we know, have the potential to improve the scalability of excited state ab initio calculations. But to use near-term quantum computers for this, we need to make sure the quantum circuits used are short and compact and also avoid any unnecessary calculations. We've developed new VQE techniques which use UCC operators for ab initio excited states calculations, which uses shorter quantum circuits and recovers states in isolation, reducing the measurement overhead and reducing the effects of noise corruption, at the same time giving the benefits and the accuracy of utilizing a physically motivated Ansatz. As a result of our work, we could now, in principle, exploit the advantages of real quantum computers for excited states calculations much sooner than previously anticipated. And so finally, I would just like to thank the Bearpark group and CQC, in particular, Nathan, Javier, and Mike for their guidance in my master's project. Here's a picture of us at the Christmas dinner last year. I throw back to perhaps simpler times where you can sit with more than 6 people at the pub. And on top of that, the Imperial College HPC facilities have been very vital to the simulations done in this work. And I also want to thank the following researchers who replied to my incessant email queries about their work. And of course, thank you for listening. There we are.
Okay, thanks very much. Really interesting. Round of applause for you too.
Thank you, Josh.
Let's take a look at some questions.
Sure, okay.
So the first one from Bruno is, did you try different classical optimizers and look at their effect on the ADAPT-VQE results?
Not yet. So we've only so far used the LBFGS optimizer. It's one of the things that are on the list. We will look at the different optimizers and have a look at what their effects might be.
Sure. I think he also mentions the ordering of the excitations, I guess.
Right. Yes. So
on how you're.
Yeah. So I mean, with the adapt method, we've had a brief look, only very briefly, a quick look at the order of excitations or order of operators that adapt ends up selecting. It's interesting. It mostly selects the paired doubles. Presumably, those are most suitable for recovering dynamic correlation. We're not quite sure. I think that in general, the field of how operators are ordered within the UCC Ansatz, which is not necessarily well defined, is still a field of a lot of investigations and studies. So we are also looking into it.
Sure, I think the order is definitely not well defined, and
yeah, absolutely.
Not an easy question to answer.
Not an easy question at all, yeah. But well, ADAPT seems to give you a pretty, at least within the framework of the algorithm, ADAPT seems to give you a pretty well-defined sequence. As to why it is the case, we need to look into that.
Sure. So another question from David Munoz Ramo. Is there a version of ADAPT-VQE that uses hardware-efficient Ansatz? Do you think your approach could be modified for this?
So yeah, we thought about this for a little bit. As far as I'm aware, the hardware efficient Ansatz, it's mostly just based on having the most flexibility between qubits, between entangled qubits, and so we're not necessarily aware of that. We know that the original authors have also published a qubit operator version, so we were using the unitary Pauli operator version, but they've gone for a qubit operator version, which is more operators but a lot closer to the lower level quantum circuit. So there's an element of that, but I'm guessing if there's a way of growing a hardware effective Ansatz based on operator selection, and there's some scheme of selecting operators for that sort of growth, then perhaps, but I'm not aware of any.
Okay. So one question from me. It seems to be, so you start with some well-defined spin symmetry and then find the next excited state with the same spin, and so on and so on. Have you thought about squeezing down the number of parameters in your circuit further with other symmetries? So, you could perhaps go down the route of projector spin and total spin, or you could go down the route of point group symmetry and spin combined.
Absolutely. That is one of the things that we will certainly look into. Well, first we want to sort of identify, like I've described here, whether or not there is some underlying symmetry constraints that we didn't account for that is being applied here when it's trying to do adapt, which made it avoid the pi symmetry. But yes, on top of that, certainly adding other constraints can simplify perhaps a number of, it will add to the number of measurements perhaps, but it will simplify it will reduce the number of parameters that we need to contend with in the final variational optimization. But selecting those operators will probably involve adding more measurements. Sure.
Okay. I mean, so for the
any other questions?
The problem that you have with the symmetry thing, I think that maybe you missed the doubly degenerate state, because the irreducible representation of the excited state is different to the irrep of the reference state. Or at least that's my first thought, is that's why. But maybe we could talk about that in more detail. And your point group stuff can be got from the orbital symmetries of your reference orbitals. Can you hear me still, or is my internet gone dead? Oh no.
Oh, hello.
Hello, was that me, or was that you, or was that?
I think that I'm afraid that was I've lost you a little bit there. Not quite sure what happened, but
okay. Can you hear me still now?
Yes, I can hear you now.
Okay, great. So I don't know where we got up to.
No, it was with regards to your symmetry question. Yes, we can add more constraints. That was the last thing. I'm trying to look on the Slack to see if there are more questions, but doesn't seem to be.
Okay. I think everyone could hear me apart from you.
Oh, really?
By the look of it, yeah. So I was just saying that I think perhaps your issue is that your excited state doesn't have the same irrep as your reference state.
The excited state doesn't have the same
irreducible representation as your.
Oh, yes, that's right.
So you probably wouldn't find it, but I don't know if that's true, given that you don't start out with the symmetry constraints, the point group symmetry constraints. I'm not sure. That's an interesting question. We could probably talk about.
Yeah, it's probably something within the spin reference that we've chosen. Maybe it inherits the spin references symmetry, but then it doesn't explain, for example, why when we did the k-UpCCGSD with k set to 2, that we do manage to get the triplet degenerate state in that case. So some interesting thing going on there.
Yeah, sure. Need to think about it in more detail.
Yes.
Probably down to some weird orbital symmetry thing.
Yes, it has to. It probably is. And like I said, it's a linear system. Oh, perfect. Yeah, I think I'm through now. I think there's another question, isn't there?
Yeah. So you said that adapt selects mostly the pair double excitation operators to recover dynamic correlation. Did you try more complicated systems and see if the pattern is quite general?
Oh, not yet. I mean, this lithium hydride was already quite a big load for now. So certainly we are looking at extending it to not only the increasing the size of the basis set, but also larger molecules as well. So yeah, but this is more of a proof of concept, just to show that we can indeed reduce the circuit depth for excited states.
Sure. And I also think I reflect Bruno's statement about static correlation rather than dynamic necessarily.
Yes.
That also depends on the state that you're looking at. So in H2, it's all static correlation pretty much in the double excitation.
Yeah. And I suppose, well, this is again in our case, this is a single reference method, right? So perhaps some of the correlation that you would get from sort of multi-configurational calculations, this method probably wouldn't recover it. But we're not sure.
Sure. Okay, great. Well, thanks very much. Great answers, great talk. I guess the discussion will continue in the
on the Slack. Great. Thank you, Josh.
All right. See you later.
See ya.